People are often surprised when I tell them the number one danger to any future manned mission to Mars is not the takeoff or the landing, but the 250 days spent patiently waiting inside the metal box. During these 8 months of travel, future astronauts will be exposed to radiation levels 50 to 100 times higher than what you or I receive here on Earth. My thesis is to work with NASA to protect them from this. In the 100 years since we discovered radioactivity, we've learned a lot about the negative effects of radiation on the human body. Thankfully, here on Earth, we're pretty well protected. We have an atmosphere 300 miles high, which has a thickness density equivalent of 7 feet of lead. In addition to that, we have a magnetic field that deflects all of the most powerful particles. But once we slip the surly bonds of Earth, all that we have for protection is what we bring with us. NASA engineers have to address this. How much is enough? Too little, and we don't protect the astronauts. Too much, and we can't get off the ground. So what materials do we use? Does the geometry of the spaceship matter? These and hundreds of other questions are what NASA engineers have to answer quickly and accurately. To do it quickly, NASA engineers use a program called Thesis. Thesis is a good, fast program. You put in your data, and a couple hours later, it gives you a dose. However, to make it that fast, they have to use a lot of approximations. And because of these approximations, they aren't totally sure how accurate this is. If it says, for instance, 6 millisieverts a day, is it 6, 2, or 20? They don't know. But we have two options to check this. The first option is to send someone into space and see how much radiation you get. I've been told that's dangerous. The second option is my thesis, and it's to build the most realistic model we can of deep space. We input the radiation, the shielding, the geometry of the spaceship, and even the human body. And what we get, although it takes longer, is much more accurate. Using that as a baseline, we can compare it to Thesis and know how close or how far it is from the true value. The code that we're going to use is called MCNP6, and is a descendant of the first program used to build the atomic bomb in the Manhattan Project. We know it works. In addition to that, we have probably some of the most realistic and detailed human-computer models, we call them phantoms, in existence. They have 41 million voxels and 86 distinct tissues, so we can get an accurate dose estimate of every organ. Using these dose estimates, we can then give NASA engineers error bars on Thesis and allow them to make quick and intelligent decisions on shielding. After that, all we have to worry about is the takeoff. Thank you.